Welcome to AI with Justin. This video is part 1 of 2, where I'll be walking through a high-level history of LLMs and VLMs to date. I made this interactive timeline to guide the video. Link for that is in the description. And I'll be adding graphics and commentary as I walk through it all. This series is also available in written form on Medium. Link for that is also in the description. And lastly, part 1 includes up until the end of 2020. Let's get started. Only 6 years ago, attention is all you need invented the transformer and caught the attention of the entire AI field. While they didn't introduce attention itself, they did introduce self-attention and multi-headed attention, and they showed that it had a lot of potential, but maybe then nobody quite understood just how much. A bit less than 1 year later, Elmo was released, which would be the last notable non-transformer based architecture. Elmo used a collection of LSTMs and was notable because it had a number of parameters which was large for the time, showcasing that researchers were already interested in scaling the size of their models, but they were restricted by their use of the less parallelizable recurrent networks as their base architecture. Then, 1 year after attention is all you need, LSTMs passed the torch to the transformers as OpenAI released GPT-1. Notably, GPT-1 was first pre-trained in unsupervised fashion, then fine-tuned for each specific benchmark or task in a supervised fashion. This pre-trained, fine-tuned strategy would become the paradigm of focus over the next period in LLM research. A few months later, Google released BERT, which was also transformer-based and followed the unsupervised pre-training, supervised fine-tuning paradigm, but varied in a few points of interest that generated a lot of discussion and motivated future research. Firstly, BERT used an encoder-only architecture, whereas GPT-1 used a decoder-only architecture. Secondly, whereas GPT-1 used only next word prediction, BERT used a combination of two unsupervised objectives during pre-training. Firstly, a next sentence prediction objective, where the model predicted whether two given sentences were sequential or not. And secondly, a fill-in-the-blank objective, making the case that each token is dependent on context from the entire sequence, both context prior to the token and after the token. Speaking of context, one shortcoming of the original transformer was that it had a fixed context length, so potentially valuable context outside of the context window would not be considered by the model. At the beginning of 2019, Transformer XL was released with a popular method of mitigating this issue. The modification used a recurrence mechanism driven by two separate streams of information. Essentially, the embeddings from the previous segment were merged with the current segment's embeddings. To make this work, the authors came up with a method of integrating relative positional information rather than absolute. 1 month later, the second GPT was released. This was a direct 10x scaling of GPT-1, meaning no significant architectural or training changes. Despite having no technical innovations, GPT-2 was notable for a few reasons. One, it showed that researchers were beginning to understand and fully commit to the power of scale. Two, GPT-2 performed fairly well on tasks without any fine-tuning, implying that perhaps generalist models were possible and maybe that emergent behavior was natural with scale. Notably, GPT-2's weights and dataset were not released, citing safety concerns, and likely partially due to increased business competition. That same summer, Google released XLNet, which had a couple interesting innovations. Namely, it used a permutation language modeling objective, or PLM, for its unsupervised pre-training. PLM is similar to the fill-in-the-blank objective used by BERT, but uses masking techniques to do this in a regressive manner, meaning it uses its previous predictions as input to its next predictions. Notably, XLNet used Transformer XL as its underlying architecture. Also, XLNet ablation studies found that next sentence prediction, as seen in BERT, was not valuable to performance. Later that summer, Facebook released Roberta, which was basically just BERT trained on more data without next sentence prediction. They reported that BERT was undertrained and seconded XLNet in the claim that next sentence prediction isn't productive. Also in July, incentivized by their desire to scale, OpenAI partnered with Microsoft and received $1 billion in funding. Note that this was not an acquisition. While there's no exact point at which top research labs became less open with their research, I'll mention now that around this time, fewer models were open sourced and technical details began to be more restricted from OpenAI and other top research labs. At this point in LLM history, the memory footprint of LLMs was beginning to exceed the capacity of individual GPUs. In September, NVIDIA released Megatron LM, which scaled the GPT-like architecture to 8.3 billion parameters. The model showed increased performance, and the research paper showcased their techniques for model and data parallelism. Observing the trend that many users and researchers lack the resources to train and utilize LLMs of such scale, Hugging Face demonstrated the use of distillation, where a smaller model is trained to mimic the behavior of a larger model. In this experiment, they showed that distillation could produce similar performance using a considerably smaller distilled model. By the start of 2020, it had been clear for a while now that unsupervised transformer-based training paradigm combined with scale had great potential. OpenAI released a paper with insights outlining what they believed to be the relationship between model architecture hyperparameters and performance as they were scaled. Notably, this relationship followed a power law. Also at the start of 2020, Google released Mina, which was intended for dialogue tasks and the first major model to prioritize human value alignment. Among Mina's pre-training corpora was 341 gigabytes of text from public domain social media conversations. Mina was fine-tuned on a human-annotated evaluation dataset, which was created according to a sensibleness and specificity average metric. Mina began as a personal project at Google and would eventually evolve into Lambda, which we'll hear more about in Part 2. The next month, Microsoft released Turing NLG, which claimed the title for most parameters, doubling Megatron LM. Microsoft also open-sourced the framework and optimizer used to train it, which would become popular among researchers. Later that month, Google released T5, an accompanying paper with tons of valuable insights and ablation studies. Some of their findings included that span predictions are more effective than single token predictions, insights on the trade-off between model size, training time, and number of ensembled models, and that given fixed compute, encoder-decoder models generally outperformed decoder-only models. In May, OpenAI released GPT-3, dwarfing all previous model parameter count by an entire order of magnitude. GPT-3 used essentially the same architecture as GPT-1 and 2, with the exception that sparse attention was used, but displayed drastically improved performance still. OpenAI cited keeping the GPT architecture because it is straightforward to both sample from and compute likelihoods with. The model could perform near state-of-the-art on many baselines without any fine-tuning, and if provided examples or useful context in its prompt, could produce some task-specific state-of-the-art results, again without any fine-tuning. Notably, in their technical paper, they provided the following insight. Scaling pure self-supervised prediction is likely to hit limits, and augmentation with a different approach is likely to be necessary. Promising future directions in this vein might include learning the objective function from humans, fine-tuning with reinforcement learning, or adding additional modalities such as images to provide grounding in a better model of the world. Each of these suggestions which would become central objectives of the research field in the following years. Doubling down on their support of learning objectives from human and inclusion of RL, OpenAI published a report on a fine-tuning technique titled Reinforcement Learning from Human Feedback. This technique used a human annotated dataset to train a model which predicts human preferences. This preference model could then act as an environment in a reinforcement learning setting to optimize a natural language generation model for an approximation of human preferences. It is this technique which led to the polished ChatGPT, which will be discussed in part 2 of this series. That's it for part 1. The link for part 2 is in the description, as well as my sources and citations. Thanks for watching.